Greetings Calc 2 students. This video is for Chapter 9 and we're going to talk specifically about the initial value problem. The initial value problem often gets called the IVP for short, initial value problem. So what's happened is we're given an initial condition, y of a equals b. So an initial condition comes from an observation. So what's happening at a particular point in our function that we're observing. So often this comes from like time. When time was equal to 0, the height of an object was something. Or when time was equal to 0, the amount of people infected with a particular disease was equal to something. So those initial values often come from observations. And we use this initial condition to find that integrating constant. That's the general purpose of initial condition, is now instead of having a solution to the differential equation that involves this plus c, we can precisely figure out the specific value of c given a specific initial condition. As a bit of a little review, it's important to remember that in this equation y of a equals b, that the a is the input, and if we're using x and y, the a would be the x, and the b is the output. So when we put in x, we get out y. So that's often important to remember, that the a is the input, and when we put in a, what does our output look like? So our b would be our output. Okay, so let's look at this example. We want to find the solution to the differential equation that satisfies the given initial condition. And our differential equation is dp, so our function name is p, with respect to time when we take its derivative. So dp dt is equal to the square root of p times t. And we're given the initial condition that p evaluated at 1 is equal to 2. So right away I have to remember that the t input in this case is equal to 1, and the p output evaluated at 1 is equal to 2. That's what that means. Now I worked out the solution ahead of time, and I found that the solution is 2 times p raised to the 1/2, or 2 times the square root of p, is equal to 2/3 times t raised to the 3/2 plus this integrating constant. Now our goal is going to be to use this initial condition when t is equal to 1, p equals 2, to figure out what this integrating constant is exactly, and then we can solve specifically for what's happening when t equals 1 and p equals 2. So then what I'm going to do is remember t equals 1, and wherever I see I'm going to put t, I'm going to put a 1. And remember that p equals 2, and wherever I see a p, I'm going to put a 2. So 2 times p, but p is equal to 2, raised to the 1/2, is equal to 2/3 times t, but t is equal to 1, raised to the 3/2, plus the integrating constant c. And now all I have to do is solve for this c. So I could write this out as 2 times the square root of 2, that's what 2 to the 1/2 means, is equal to, and then 1 raised to the 3/2 is just going to be 1, and so I'm left with 2/3 times 1, and that's plus c, my integrating constant. So when I solve for c, I get root 2 times 2 minus 2/3 is equal to my integrating constant c. So then I just take my solution. I have 2p raised to the 1/2 is equal to 2/3 times t raised to the 3/2 plus c. But c is equal to 2 times root 2 minus 2/3. And once again, what I did was took this c and plugged it into my solution and rewrote it out. So this c got plugged into my solution. Now what I want to do is figure out how to solve for p. So I want to write this function in terms of p. So I'm going to divide everything by 2, and when I do that, I get p raised to the 1/2 is equal to, divide everything by 2. So 2/3 t to the 3 over 2, divide that by 2, plus 2 times root 2 divided by 2, minus 2 over 3, divide that by 2. And when I simplify that, I get p raised to the 1/2 is equal to 1/3 times t to the 3 over 2 plus root 2 minus 1/3. And then finally, I'm going to square both sides to get the p all by itself. So p is equal to 1/3 t to the 3 over 2 plus root 2 minus 1/3, all of that squared, and that's equal to my function p. And to make it look really nice, what I would tend to do is write p as a function of t, so actually write it out this way, is equal to the t to the 3 over 2 divided by 3 plus root 2 minus 1/3, that whole thing squared. So my final answer is this p as a function of t, specifically with the value of c found from my initial conditions. When t is equal to 1, the function evaluated at 1 is equal to 2, and I have this final answer. P of t equals t to the 3 over 2 divided by 3 plus root 2 minus 1/3, quantity squared.